Alright, so I'm going to be looking at problem 5.14, which is a steady current flows down along a cylindrical wire of radius A, as shown in this figure, and we're asked to find the magnetic field both inside and outside the wire. If the current is uniformly distributed over the outside surface of the wire, and if the current is distributed in such a way where J is proportional to S, so it's a current density in that case. So we'll first set this problem up. I've drawn separately here a different orientation with sort of what we want to do here. But basically, we want to create two Amperian loops, one inside and one outside of this cylinder. And we'll look at it by cases. Each part will have two cases. One where the radius of the Amperian loop, which we'll call S, is less than A, the radius of the cylinder, and then one where it's greater than A. And so let's begin part A. Let's do that here. Part A by looking at first how we'll set this up. We'll begin with invoking Ampere's law, which is that here the closed loop integral v dot dl is mu naught I enclosed. So due to the symmetry of this setup here, the Amperian loops will actually be experiencing the same magnetic field in each part of the loop. So we can actually rewrite this as B times the integral of dl, where dl is actually just S d phi, because we're just looking at here the radius, and then this is what we're rotating around, which is phi. So we want to do a full rotation, so we go from 0 to 2 pi, and that results in us getting B times 2 pi radius, which equals the mu naught times I enclosed. And now if we look at the S is less than A, well, for B there is no I enclosed, because this is a surface current. So for this case, we're going to end up getting 0. So when we look at the magnetic field here, just ends up being 0 for this case. And then for greater than A, so on the outside, so this loop right here, we just divide by the 2 pi s, right? So we get mu naught I over 2 pi s. And now we want this to be a vector. This is just the magnitude. So we just use the right-hand rule. So I forgot to draw that initially, but this would be where the current is pointing in this case. So use the right-hand rule, and you see that it is rotating along phi, right in the phi direction. So that means that if we want this to be a vector, then it points in the phi hat, where I enclosed for the outer loop, I'm making it look like it's for the previous case, where I enclosed is all of I, the whole current is what we're looking at here. So it's just I. And so this is the answer to part A for the two cases. And now we'll look at part B. And part B will be ever so slightly more complicated. With part B, we have a current density. So we have J, right? J proportional to S. So J equals Ks. And the first thing we want to figure out is what that K is. And so what we'll do is we'll use the formula for current here. So I equals integral of J dA, which this becomes a double integral right? J is K S, and dA area in cylindrical coordinates here, we'll be looking at S ds d phi, and then to figure out our limits with d phi, we know that we're doing a full rotation here, 0 to 2 pi, and then for changing the ds, we're going from 0, because we're starting at the axis. We're going from 0, and then we're going out to the radius of the cylinder, which is A. And so this is the integral that we need to use to find a current. So here we'll end up with 2 pi Ks to the third from 0 to A, and that will just be 2 pi K A to the third over 3. And so if we want to find what the constant K is, we can move it over, and we'll get that K is equal to 3I over 2 pi A to the third. Now we can look at our two cases. So for our radius less than a, so the inner loop, again, recall Ampere's law, B dot dl equals mu naught I enclosed. Well, here, if we just want to, we have to solve our I this time around. So we will, again, doing the same steps as before, we know that B, magnitude B times 2 pi S is what we end up with due to the symmetry of our setup. And that will equal mu naught times, this time we do a double integral here of and then for this part we can call this S prime or R if you prefer, but it'll be some radius S prime ds prime d phi I use S prime just to remind me that I'm integrating S into this, because we're going from 0 to S for the ds prime, because we're varying our radius here from 0 to the radius of the loop, and then the d phi, same as always, just 0 to 2 pi. And so when we integrate this, we'll get mu naught outside, and then 2 pi sorry, 2 pi on the outside, k S prime to the third over 3 from 0 to S, so we get 2 pi mu naught, just incorporated the mu naught, S to the third, now I plugged in the S, over 3, keep in mind k, we have a definition for it already. So for k, you can plug in 3i 2 pi a to the third, like that. And then multiply these and divide by the 2 pi s, and when you do all that, you should end up with mu naught, so this would be b, mu naught I s squared 2 pi a to the third and let me just verify real quick. Right, because we divided by the 2 pi s, so an s went away. Yes, this is Correct. So we have this. We turn it into a vector. Again, right-hand rule. Again, still pointing in the same direction. So we're going to be rotating around phi. This is the answer to this case right here. And if you then want this case, well, for this case, the answer is actually going to be exactly the same as for part A, because it's still the whole I that is enclosed. So the loop is still around, the Amperian loop is still around the same I. So in this case, it's just by Ampere's law. This. And so, let me pull this down. These are our two answers for part A and part B. Or rather, sorry. This one and these.